Hello, welcome to another update video for DeepFX Studio. I don't have anything visually impressive to show you today, but I wanted to delve into the other side of DeepFX Studio, which I haven't really shown in the new version I've been working on. Today I will just look at nodes, essentially, and the functionality, the philosophy, of what's going on behind them and what I've been doing. Okay, so for a while I don't think there'll be updates on anything visually interesting. I'll be working on the back end for the nodes, so basic logic stuff like that. Try to get it on par with the old version that I'm rewriting. But the good news is things will be changing. I think I talked about the new, if you look back in the videos, about the philosophy of the new Fluent editor. So it's event-based, so I think I talked about this. So for each keyframe, an event, for example, will be shot out, and then you need to execute a block of statements. And within that statements, there's flows. Okay, and a flow is simply a flow graph. Okay, so you've got a process and a decision. So the flow graph represents the condition of the program. So this is where you'd make your decisions. If, for example, you wanted this group of particles to go in that group of particles, you could do that here, for example. All conditions will be handled here. So the flow of or the logic or whatever would go here. I did this because I wanted to make things more visible. Okay, so like a flowchart example. So you could plan your whole algorithm, whatever simulation right here before you even get into the compute nodes, and get the basic logic out of that. So there's nothing special here, it's just it goes per block. So for each process, you've got a number of processes. I call them compute nodes. So we go down then, and decision. Your compute graph would spit out a true or false statement. So should I go down this path or go along that path? So basic stuff right there. So the true power though is within the compute nodes. This is what I've been spending some time on for the past couple of weeks. I just wanted to show you what I've been working on and the philosophy I've been taking. So there's a lot of styles when it comes to visual programming. So I've been studying a few things like Houdini, ICE, Bifrost, and like Maya. A lot of stuff actually. Lightwave's got one as well. Blender's getting one. I think it's called Nodes Everything in the future. So everybody's actually taking the node workflow seriously. So I decided to upgrade the node flow to take it a step forward. So into more programming realm. Okay, it's going to become more visual programming than just linking than a data flow, for example. It's not just going to be data flow. We can actually do programming things. So for example, this would be a conditional statement right here, and then everything else would be in your compute nodes. And so since I know a few languages like Java and Haskell. Haskell is one of my favorite languages because of the functional nature. I like it, but I can't be productive in it. And other people can, but I've tried it, but I like the ideas behind it. So I decided to take a big portion of functional programming because I thought it was very concise for visual programming. So, and you see this pretty much in the iteration data structures that will be in DeepFX Studio. Okay, so I borrowed a lot of this from Java and Haskell. Well, technically Java borrowed from Haskell and stuff like that, okay? But I'll explain what this means right here. So in iterations, you will have several structures, code for each, filter map, partition, peak, reduce. If you're familiar with functional programming, you probably heard of the design pattern map reduce. So it follows that and just expands on that. So this is mainly just for arrays. So arrays will be getting expanded in the new one. So I'm just gonna start with something very basic here. I'm gonna a new array node here, and you will notice two things now. You can inputs can be dynamic on some nodes, not all nodes. So the white color now means universal. You can plug in anything into the white ports, and if the node accepts whatever goes in it to spit out stuff for you. Okay, so for now I'm just going to do something very basic and just build a quick string array, for example. 1, Again, obviously, I'm taking inspiration from what's existing out there to make things more powerful. Of course, to stay modern but still different. I don't think anybody does this like this. I could be wrong. Of course, I haven't gone to every visual programming program to see what they're doing. So I think I saw the Unreal Engine. That was pretty versatile, but I didn't have time to actually delve deep into it. I knew what I wanted at some point. Okay. So yeah, the functional nature. As you can see, for each node, there'll be this slot called the functor. Functor in math is just a function that takes something and maps something to into a domain or something. But in this case, it will be generic for any type of compound node, essentially. So you need a compound node, and then you will need to give the compound node a signature. So just like a real programming language, your compound nodes can now become like real functions, and you can feed these nodes into your iterators. Okay. 1 second. Let me get this into place here. So I just want to print out some string of arrays. So I'm gonna just connect this out to the compound. Okay. And once we've got that, that's all we need. Then you need to specify that the compound node will be functional. What this means is it won't be executed at all. Okay, so it will be ignored during the execution of the compute graph. And yeah, so if I just press forward once, I need to give the string something, so I will just do a short message. And there we go. So it will loop through the array I'm building here, and it will map this function, obviously the compound node, which I've turned into a function, and I've piped into the for each node there, and it will spit out the data for you. So that's how iterations will be handled. So I think this is very intuitive. Okay, as in all your logic can be in here. So for example, if you want to do something like a wrangle node, you won't need a script, for example. I think this is very convenient. Okay, if we follow this design pattern for the graphical nature of it. So that's the first part of this. Is very straightforward, as you can see. It just took me a few connections, and all you have to do is just match the signature. So that's the inputs and outputs for the compound node, and the documentation will be very clear about this. It's very straightforward. So yeah, so all the for each does is maps a function to it, so there's no output for this, for example. So we can move on to the next one. Okay, now moving on to the map node. Like I said, this will be used to map one array into another array. Okay, we will use a range node for this. So range node, all it does is just create a range of values between the minimum and maximum. Straightforward. Then of course we'll need a compound node to map the values for this. So it's very straightforward as well for this. So we will do a multiplication. We'll multiply by 2. Every value in the array by 2 and spit out the results. Okay. And as you can see, the dynamic values will come in handy for things like the multiply node, where it makes sense for that. They won't be on everything. If it makes sense, you'll be able to add values dynamically like that. Of course, it's a temporary thing, of course. For example, if you delete a connection, it will erase that value. Just obviously, it's just a common sense thing. Okay, and then we just multiply everything by 2, like that. Okay, and just turn that into a functional compound array. So just do this to see if we get any errors. There's no errors, so we'll assume everything went well. Then again we will need the for each loop just to print everything out. Of course there'll be utility functions at the end of this. You won't have to do this for everything, just for example's sake. Okay, so 1 second. We just need a decimal to string like that, and then a console out. Yeah, that's pretty much it for that. So we can just plug that in and the array right in, and you can just go one frame and we'll get our numbers. So it's that straightforward. And I think as things develop, the compound nodes, simple things like these compound nodes will be put into a library. Okay, so just for quickly applying maps and for each loops and anything in the iterator section. I think if it makes sense, it will probably appear there. Yeah, so you see, so that's what the mapping function is for. Okay, I can look at another example. I'll just go through all the iteration types. Another good thing about doing things like this, you can modify values in place, so you won't need variables. So if C++, Java, Python, whatever, if you want to loop over something and modify it, you need to put in a variable first and spit it out. But the good thing about doing iterations like this, you won't need any temporary memory handling. So you can skip that step completely. Of course, you'll be able to create attributes dynamically and write to them, but I think that would have been more tedious than actually doing it like this. So that's another good thing about this. You get to do everything in place. And this will make really sense when we do the reduce, for example. We'll do the filter next. The filter is a bit different. I'll just show you that. The signature is a bit different. All it does is returns a true or false statement. So you give it an array. You do something. You test the array. I don't know. You want to check if a particle is a certain age, etc. And then if it is too old to kill it, you say yes. Else you don't kill it. And then it will filter out everything that's false and just keep the true values, for example. So it's also straightforward. We're just gonna use a comparison for this. So I'm just gonna say less than. Straightforward. So we're gonna say if A is less than a certain value, less than B, we'll say that is true. So if A is less than B, so we want all the values that are less than 5 there, okay? Yeah, that's about it. We can plug that into the functional. Then we just need an array. We'll use the range node again, just to do it quickly. You can always use the build node, but it's more tedious doing that. Just make sure it starts at 1. Of course, it won't give any errors. We will need to do this again. 1 second. Actually, should have kept that one in the last section. Since all we're doing is just printing out floats. And I can see the proof again. Small little bug there. I know, it will be ironed out by the time everything is completed. Okay, so we just plug that into there and the output into there, and we can do that. So yes, as you can see, we only get numbers 1, 2, 3, 4. Based on the condition we gave. So less than 5, we get that. And then, for example, let's say you wanted to keep both. You don't have to do this twice. We've got a convenient iterator called partition. So partition is exactly the same as filter. But instead it will return both. It will partition the results for you, the true and false for that. So I can just show you that quickly as well. We won't need to change anything. And just it's essentially the same thing. So the second half of that, print out that, it will give us 6. 1 second, is that correct? Yeah, 5, 6, 7, 8, 9, and 10. And we can just confirm that by plugging in the first one there. It's 1, 2, 3, 4. So yes, that's what the partition node is for. It's exactly the same as the filter node, but gives you both values. Okay. Next one, peak. Peak is map. Sorry, peak is a for each, but it will return the same array you feed into it. So this is just good, helpful for keeping the flow of the compute graph. So instead of putting the for each on top just to print out stuff, if you're not sure which node to execute first, you can use the peak. So you can execute some functions, pass the same array through, and continue. So that's what the peak node will be for. And then I think we'll just look at the last one, which is reduce. Now reduce really helps. It helps that you can do everything in place. So for example, let's say we didn't have variables or they were very inefficient, reduce makes a lot of sense. So the signature is a bit different here. Should get reduce. Okay. So we need a new compound for this. It's got a different signature from the others. So it's got A and B. It takes two values. It takes the value from the array and the accumulator. And the accumulator is just the same value that you modify in each step of the loop. So for example, if you wanted to sum everything, it's just the sum. The sum would be the accumulating sum, for example, would be the accumulator for that. So we need, so the first argument would be a value from the array. And the next value would be the accumulator. Okay, I'm sure if you've worked with these constructs before, this makes perfect sense here. Makes perfect sense. Okay, it's straightforward for you. They're just going to multiply these two, essentially. 1 and 2, and then I'm just going to speed out the value for that. So we're just going to do accumulated multiplication. And so we'll put that into reduce and that into there. So, and another thing, if I try to play this, we'll get an error here. You need an initial value for this. So, the first value. So, it will be used in the accumulator. So if the array is empty, to just return the initial value. Sorry, not that. We need a float value. Yeah, okay. So since it's multiplication, we'll just make it 1. Yeah, that's about it. And this just returns one value now. So what we can do, let's just get rid of these lengths over here. And just do a just matrix 3 and it comes out. So this will just give us one value there. There you go. So the sum of everything from 1 to 10, I mean accumulating multiple, of course, will be that number there. So it's that straightforward. And you can mix and match these things as much as you want. But there is one limitation to keep things sane, of course. Since this is not a full programming language, we will not be having recursive functionals. So you cannot have nested functions or compounds in what you call it in the functional compound. Sorry. The reason is very simple. Even in C++, if you've got a big recursion stack, it will crash the program. So to avoid things like that, it's just going to. We're not going to do that. I think the only language that actually does that really well is something like Haskell. I think you can build really big, infinite numbers just by infinite recursion. So that's something interesting. But it's a functional language. There's no such thing as mutable type. So everything has to be recursive in that language, for example. If you're interested in programming, I highly recommend just playing around with that if you're interested in stuff like this. So I've borrowed a lot of stuff from that. So that's it. So I've just covered iterations for this. So that's what I've been working on. Surprisingly, that wasn't as straightforward as I thought it would be, but I did it. It's in there. So we'll be able to do this to make things more easier and more, more like a programming language. After that, I'm just going to work on some optimizations, then I'll add some more nodes, and then at some point I'll post another update. So if you don't hear anything from me, I'm doing some back-end stuff that's not really interesting like this. I guess if you're an artist and you're not interested in programming, you can skip this video. But if you're really interested in this type of thing, I'm sure you would have enjoyed the technical talk and stuff like that. Yes, so I'll continue improving this, and thank you for watching, and yeah, I'll see you in the next video.